স্যার স্টার্ট করি।
হ্যাঁ করো।
Good afternoon, everybody. A warm welcome to all of you. We have eagerly waiting for this seminar. Today, the day has come. The topic of this seminar is different aspects of chemistry in our daily life. So, before we begin, I would like to convey my heartiest thanks to and gratitude to everybody to joining this seminar to make it beautiful and success. We are extremely grateful for your teachers. Without their help, it is impossible to organize this
ভাস্কর দা
seminar.
একটু মিউট করে দাও। ভাস্কর দা তোমার সাউন্ড একটু মিউট করো, নয়েস আসছিল।
Due to
ওকে,
due to some important reason, our honorable principal sir is absent today. So I earnestly request our respected HOD to say about this seminar. Please, ma'am.
Thank you, Nilanjana. Good afternoon, everybody. Today, our beloved students of our Department of Chemistry of Navadvip Vidyasagar College are going to organize a webinar entitled Different Aspects of Chemistry in Reality. I am very much delighted to have this opportunity to say something before you on behalf of our department. Uh, First of all, I offer my heartfelt thanks to all teacher and student participants. Unfortunately, we are missing our honorable principal, whose constant support and inspiration has driven our college, our institution to achieving academic excellence. He could not be present here today due to his busy, hectic schedule throughout the day. But we are thankful to him for his consent and good wishes for our seminar. Uh, Actually, it is very difficult for our students to manage a convenient time slot for organizing this webinar, as they are almost sandwiched under the huge pressure of ceaseless motion of online classes, assignments, and exams. But in spite of all these burdens, their wholehearted attempt in this regard must deserve a special mention. So those who will deliver the lectures today, those who will patiently listen to them, and those who will interact with them, and those who will conduct the program with great endeavor are the most welcome. I am thankful to my esteemed colleagues of department, Professor Pankaj Sarkar, Dr. Bhaskar Chatterjee, Dr. Somashet Dule, and Professor Monisha Dash, who have constantly inspired our students and helped our students with untiring efforts to prepare their lectures and extended their helping hands for technical support. Now I would like to say something about the seminar, this seminar or webinar. In the development of modern science, chemistry has always played a key role to bridge the various branches of natural science through different aspects of its subdisciplinary fields like organic, inorganic, physical, analytical, biochemistry, green chemistry, environmental chemistry, etc. The unimaginable growth of chemistry in the last few decades due to extremely high quality research contributions of eminent scientists working in the frontal area of chemistry, as well as other related subjects of both fundamental and applied nature like life science, biotechnology, nanoscience, medicine, agrochemicals, etc., enabled chemists not only to construct new molecules and molecular assemblies of diverse shape, size, and complexity for studying their interesting and useful properties, but also to understand various intricate scientific phenomena of complex biological and material world. The properties of those newly constructed molecules have tangible benefit for society. So chemistry has got wide applications in every sphere of life, uh, the enormous development of chemistry has constituted huge volume of chemical literature. So our students are primarily acquainted and enriched with the knowledge of basic and some important and many important aspects of chemistry in UG courses, so that they can prepare the strong foundation for higher studies and chemical research. And uh, uh, it is all of you know that seminar or webinar is a suitable platform for cultivation of knowledge beyond classroom teaching learning. So our students have organized this webinar to present before all of you their deliberations on various topics of different aspects of chemistry, and you will listen to them shortly. And I hope all these deliberations will be highly appreciable, and it will evoke considerable interest among the students, and it will build up strong commitments among all participants. And lastly, I convey my best wishes to all of you and wish the grand success of the webinar. Thank you all.
Thank you so much, ma'am, for your valuable words. And now it's time to begin our seminar. And I wish that the seminar will be very fruitful for everybody who are present here. Our first participant is Damayanti Roy from 5th Sem, and her topic is spectroscopy. I request her to tell something discussion. Please.
Good afternoon, everyone. My name is Damayanti Roy. I am a student of Chemistry Department of 5th semester of Navadip Vidyasagar College. The title of my topic is Luminescence. So let's get started with what is luminescence. Luminescence is the optical property of materials which consists of emission of visible light under irradiation with UV radiation. The word luminescence is derived from two Latin words lumen and essentia, which means light and the process of respectively. Hence, luminescence represents the process of giving light. Classification. Luminescence can be classified into various categories depending upon the source of energy. Photoluminescence, absorption of photons. This can be categorized into fluorescence and phosphorescence. Cathodoluminescence, bombardment by electrons. Chemiluminescence, initiated by chemical reactions. This can be categorized into bioluminescence, electroluminescence, candoluminescence, and lyoluminescence. Electroluminescence, applied electric field. Mechanoluminescence, through mechanical action. This can be categorized into triboluminescence, fractoluminescence, piezoluminescence, and sonoluminescence. Radioluminescence, bombardment by ionizing radiation. Thermoluminescence, activated by heating. Here comes the main discussion part, fluorescence. Fluorescence is emission of electromagnetic radiation, usually light, caused by excitation of atoms in material, which then re-emits almost immediately. The emitted light has a longer wavelength, therefore lower energy than the absorbed radiation. Materials, fluorides, petroleum, the organic dyes like eosine, fluorosine, compounds like chlorophyll, ultramarine, riboflavin, etc. exhibit fluorescence. Sensitized fluorescence. Fluorescence may also occur without direct absorption of light but being excited with the help of foreign material. Atom of one species, called donor, is excited radiationally and then transfers its excitation energy to an atom of same or another species, called acceptor, by collision. The acceptor then undergoes radiation deactivation, resulting in sensitized fluorescence. The process can be represented as A plus HU gives A star plus B gives A plus B star gives B, plus h nu f. Quenching of fluorescence. Sometimes, in presence of some material, the rate of fluorescence is decreased. The intensity of fluorescence radiation is diminished when a photochemically excited atom collides with another atom. This is known as quenching of fluorescence. For example, chloride ion is well-known quencher of quinine fluorescence. Phosphorescence. In luminescence study, the term which parallelly comes in our mind while studying fluorescence, that is phosphorescence. Phosphorescence is a process in which energy absorbed by a substance is released relatively slower in the form of light. Phosphorescence lifetime is longer than fluorescence lifetime because in fluorescence, transition occurs between same states of spin multiplicity, that is singlet to singlet or triplet to triplet, whereas in phosphorescence, transition occurs between different states of spin multiplicity, that is triplet to singlet, which is quantum mechanically forbidden. Jablonski diagram. With the help of Jablonski diagram, we can illustrate the mechanism of fluorescence as well as phosphorescence. This was proposed by Alexander Jablonski in 1935 to describe absorption and emission of light. There are two types of transition observed. Radiative transition. This is observed in fluorescence and phosphorescence. Non-radiative transition. This is observed in internal conversion and intersystem crossing. Pathway. A photochemical process passes through the following pathway. Absorption. A radiative transition from a lower to a higher electronic state of molecule. Vibrational relaxation. A non-radiative transition to a lower vibrational level within the same electronic state. Internal conversion. A non-radiative transition between two electronic states of the same spin multiplicity. Fluorescence. A radiative transition between two electronic states of same spin multiplicity. Intersystem crossing. A non-radiative transition between two isoenergetic vibrational levels belonging to electronic states of different spin multiplicity. Phosphorescence. A radiative transition between two electronic states of different spin multiplicity. Mechanism. The first step in a photochemical process is the absorption of photon by the molecule. Then the molecule is transferred from its ground state to another high state, which is denoted in the blue arrows. This is the fastest transition in Jablonski diagram, which occurs in 10 to the power minus 15 seconds. When the atom is excited, it is in non-equilibrium state and eventually decrease its energy and come to the ground state. The first step by which it loses its energy is through vibrational relaxation, which is defined in the yellow arrows, which occurs in the time scale of 10 to the power minus 12 to 10 to the power minus 10 seconds. An excited molecule may undergo from its higher energy state to a lower energy state of same spin multiplicity. This is defined as internal conversion, shown in the violet arrows, which occurs in 10 to the power minus 10 to 10 to the power minus 9 seconds. A vibrational transition from S1 to S0 is called fluorescence, shown in the green arrows, which occurs in 10 to the power minus 10 to 10 to the power minus 7 seconds. An alternative pathway of fluorescence and internal conversion is intersystem crossing from S1 to T1, which is denoted in the aqua-colored arrows. This occurs in 10 to the power minus 10 to 10 to the power minus 8 seconds. A radiative transition from T1 to S0 is known as phosphorescence. This is shown in red colored arrows, which occurs in 10 to the power minus 6 to 10 seconds. This is normally spin angular momentum. This divides spin angular momentum, but it is still possible through spin orbit coupling. Application. Luminescence has a wide range of application. In the semiconductor industry, this is used for band gap determination, recombination mechanism, surface structure, and excited states. In forensic science, this is used for locate and identify similar strains, detection of lead or antimony gunshot residue, discriminating samples of living, human and non-living systems, glasses, metals. In chemical industry, this is used for structure determination, identifying groups or aromatic compounds. Advantages and disadvantages. The advantages of luminescence is high intensity, good energy response, reusability, high resistance to high humidity and magnetic fields. The disadvantages are non-advisable for radioactive elements, non-domesticity problems, difficult to study complex systems. Conclusion. Luminescence is an important tool in science research, from the deep sea to crime lab. Everywhere luminescence has an impact. Its most common everyday application is LED lights, glow in the dark stars, glowing paint, product labeling, laser, road marks, safety sign, etc. Thank you.
Thank you so much for your discussion. And if there are any question, so please I request to ask them. Okay, I think there is no question. So our next participant is Lokesh Haldar from SEM 5 and his topic is Green Catalyst. So I request his to tell about her discussion.
Thank you. Good afternoon, everyone presented here. My respected teachers, my friends, my junior classmates, to everyone, a very good morning, good afternoon. Today, I have a presentation about the topic called green catalyst and its use in pharmaceutical industry. My name is Lokesh Aldar and I am a student of 5th semester Navodaya Vidyasagar College of Chemistry Department. So let me first introduce you with this topic. We all know that climate change is the biggest problem of modern age. And to reduce this, there is a growing need for
Lokesh,
more
your
environmentally.
presentation. লোকেশ
হ্যাঁ ম্যাম,
লোকেশ তোমার প্রেজেন্টেশনটা অন করো।
ম্যাম আমি অন করে রেখেছি তো।
Anybody can see the presentation?
কিন্তু
শেয়ার
ভীষণ ছোট
হয়নি।
স্ক্রিনটা এত ছোট কেন স্ক্রিনটা?
লোকেশ কি প্রেজেন্ট করেছো? প্রেজেন্ট নাও করেছো?
না,
হ্যাঁ
প্রেজেন্ট নাও
আমি
করার
প্রেজেন্ট করেছি তো স্যার।
কিন্তু তোমার তো কিছু দেখাচ্ছে না স্লাইড।
দেখাচ্ছে, আমি দেখতে পাচ্ছি ভীষণ ছোট, ভীষণ স্ক্রিনটা খুবই ছোট।
ওটা পিন করুন, তাহলে পিন
ও
করলে
পিন
ওটা
করলে বড় হবে না?
পিন
আচ্ছা
করলে বড়
আচ্ছা,
হয়ে যাবে।
ঠিক
আচ্ছা,
আছে।
পিন
হ্যাঁ
করলে
হ্যাঁ।
বড়।
ওকে,
ও মা, না তো কি হলো?
ঠিক আছে, স্টার্ট করো আমি তাহলে।
করো।
হ্যাঁ।
ওকে। We all know that climate change is the biggest problem of modern age. In the chemical industry, and this trend is known as sustainable technology, which is focused on economic value, which eliminates waste to at source and avoiding the use of toxic and hazardous substances. As I'm going to here, this task is multiple times, we should make with these terms. Simply, a catalyst is a substance that increases or decreases a chemical reaction without itself undergoing an and you can see how the process simply looks like. And that and the and the process in which the rate of a chemical reaction increases or decreases depending upon which type of catalyst is used is called catalysis. And they have some interesting characteristic. They decreases the energy requirement, which helps a reaction happen more easily, and it doesn't require in stoichiometric amount. That means less waste product and isolation and reusability. As they are isolable from the reaction medium, they can be they can be used multiple times. Now, whom we can call a green catalyst, or what is a green catalyst? If a substance make a chemical reaction greener, it means less hazardous or less waste product, less energy requirement, more enantiomeric access, and most important characteristic is better isolation and reusability. If a substance fulfill those criteria, then we can call them a green catalyst. There are only two types of catalyst. One is homogeneous and the second one is heterogeneous. Homogeneous means they shape or obtain the expected product, but as they are homogeneous to the reactants, they are hard to isolate from the reaction medium, so the reusability is very low. For heterogeneous catalysts, they are effective, but they are attractive to reusability and isolation from the reaction medium. Now let us see how they are used in pharmaceutical industries. Nano catalyst. These are in the category of semi-heterogeneous catalysts and have taken more attention as they have large surface to volume ratio, resulting more interaction between the surface of a catalyst and reactant with greater amount of release. Silver, gold, etc. Nanoparticles are some examples of nanocatalysts. An example of a drug that is synthesized using a nanocatalyst is xanthone. Previously, it was used as an insecticide, but it have a broad spectrum of pharmacological properties, including antioxidant, anti-tumor, anti-allergic, antibacterial, anti-inflammatory, etc. activities. And the green synthesis of xanthone goes like this way. A phenol derivative with salicylaldehyde or 2-methoxyphenol reacted with copper oxide nanoparticle with tripotassium phosphate and toluene that leads to the xanthone derivative. And this reaction some characteristics. In this reaction, the nanoparticles are used, and this is a single step reaction, and the nanoparticles are 89% effective till the fourth cycle. If we altered this nanocatalyst with conventional catalyst like CuC or CuO, that decreases the yield of the product down to 65 to 62% respectively. Our second example is quinazolone, and these large mass of biologically compounds that broad spectrum of biological activities such as anti-aging, anti-cancer, antifungal, antibacterial, etc. And the green synthesis of quinazolinone goes like this way. First, halobenzamide and benzylamine reacted in presence of copper oxide nanoparticles with potassium dichromate and DMF that leads to quinazolinone derivative. Assignment that conventional catalysts such as CuO have less catalytic effect than copper nanocatalyst. Furthermore, if you use a catalyst, then there will be no cyclic product. Now, like catalysts, biocatalysts are a particular type of catalyst, and these are biological materials which can be an isolated enzyme or a crude cell-free extract, an immobilized enzyme, or enzyme in whole microbial cell. And enzymes are critical endogens and have a vital role in living cells. sterilizes all in vivo metabolic reactions to produce the necessary product for the body. Examples of biocatalysts are protease, cellulase, amylase, etc. Now, what are the advantages of biocatalyst? The reactions are performed in organic media with protection against doesn't require. These are fast reaction and conversions are stereospecific. In this category, our first example of a drug that is synthesized using a biocatalyst is sitagliptin. It is an antidiabetic drug that works by increasing the level of natural substance called incretins, which helps control blood sugar by increasing the insulin release. And the green synthesis goes like this way. Prositagliptin ketone is prositagliptin ketone in presence of DHT or D-haloperoxidase produces sitagliptin. There is 99.5% excess and like the previous ones, this reaction is also a single-step reaction. And our second example is conversion of racemic amino acid amide to optically active amino acid derivative by lipase palladium catalyst. And in this process provides 80 to 90% yield, 5 to 98%. And our third APA or 6-aminopenicillinic acid. And this is used to non-forming bacterium such as and Staphylococcus. It is used as a precursor of the compound ampicillin and amoxicillin. And the green synthesis process is shown in the slide. There is two pathway. One is green synthetic pathway, and the other is conventional pathway, which starts from penicillin G. The green pathway in ambient temperature and within a single step, and there water is used as a solvent. And in a conventional method, we can see different reagents in steps. Multiple steps are involved in it, and very which is not a good thing. Thus, adopting the green synthetic pathway can reduce the waste of solvent and in. Now, from our in observation, we can conclude that chemistry is getting extended in many researches and industrial areas. The reason is that the resources are limited and it is necessary to be consumed with caution. Most make increasing effort to and avoid air and water pollution. Green solvent and catalyst give many opportunities for pharmaceutical for greener method in which impact on the environment and the cost of pharmaceuticals can be decreased. With advantages of green chemistry, hopefully industries will learn conventional method with greener ones. Thank you.
Thank you for the discussion. If there are any question related to this topic, so I request to ask. Okay, I think there is no question. So our next participant is Devlina Datto from semester 3 and her topic is metal reaction. So I request her to discussion.
Good afternoon, everyone. Myself, Devlina Datta. I am a student of Navadip Vidyasagar College in Chemistry Department, third semester. First of all, I would like to thank my respected teachers to give me this opportunity. It is such an honor for me. Today I am presenting you Michael reaction and its broader side. Today's discussing topic is introduction, reaction, mechanism, synthetic aspect, application, and Michael reaction in nature. Before enter the main topic, let's talk about its background and the introduction. So, Michael addition reaction has been a very classical reaction in the field of organic synthesis. It is widely used to synthesize all kinds of natural products and drugs. This reaction is named after Arthur Michael, who invented this reaction in 1887. So what is Michael reaction? Basically, the conjugate addition of a stabilized enolate ion to the activated double bond of alpha-beta unsaturated carbonyl compounds, ester, amides, nitrile, sulfonyls, nitro compounds, leading to the formation of a new carbon-carbon bond is called a Michael addition or Michael reaction. So in short, when enolate ion reacts with alpha-beta unsaturated carbonyl compound in presence of an organic base, Michael reaction has formed. This is the mechanism. It has three steps. The first step is the formation of nucleophile. Then the nucleophile is react with alpha-beta unsaturated carbonyl compound. This negative charge will attack on this carbon, and then the charge density will shift on that carbon. And for enolate ion synthesis, this charge is shift on the oxygen and will form enolate. After protonation, 1,4 addition will form, and at last, after tautomerism, the final product will form. This is the mechanism you can see. So, in the next aspect, mesithyl oxide react with diethyl malonate in presence of base, and after Dickman reaction and protonation, the final product dimidone has formed. This is the reaction. Robinson annulation reaction is a very popular name reaction. This reaction begins with a Michael reaction followed by an intramolecular aldol condensation to give a new six-member ring. So this is the six-member ring which is formed. Let's talk about Oxamical addition. In the terms, Oxamical reaction have been used to refer to the 1,4 addition of oxygen nucleophile respectively. This is the mechanism, and as like Oxamical reaction, in the term of Azamical reaction have been used to refer to the 1,4 addition of nitrogen nucleophile respectively. Here's the reaction you can see. Our next application is Thiamical reaction. The Thiamical addition reaction is an organic reaction between thiol and an ene compound with electron withdrawing group. This is the main compound and this is the catalyst, and that's the reaction. Phosphate Michael addition. Michael addition of dialkyl phosphate to provide beta nitrophosphate followed by reaction of nitro group afford beta aminophosphate as valuable bioactive molecules. This is the main compound beta nitrophosphate which is formed. Let's talk about synthesis of S-pregabalin. Pregabalin, marketed under the brand name Lyrica among others, is an anticonvulsant and antidialectic medication used to treat epilepsy, neuropathic pain, restless leg syndrome, and generalized anxiety disorder. So this is the main compound. S-pregabalin is formed by this Michael reaction. Let's talk about the uses. Michael addition reaction has been employed to prepare polymers of various architecture. Michael addition reaction have been also applied to prepare thermosetting resins like polyester, epoxy, vinyl ester, silicone, phenolic acid, etc. Now let's talk about Michael reaction in nature. In the context of the RNA world hypothesis, this pathway represents an important line how thymidine synthesis may have occurred from uracil precursors in an RNA world in which RNA molecule evolved method to produce DNA precursors. To test whether RNA catalyst could be developed for this important reaction and to provide an RNA model for thymidine synthesis, we designed an in vitro selection scheme for generating RNA molecule with Michael reaction.
Our strategy involved generating a randomized pool of RNA conjugate in which a fumarate moiety, a deactivated Michael acceptor system, is covalently attached to each individual pool molecule via a flexible alkyne chain containing a photosensitive group. So you can see this is the chart of Michael reaction in biological molecules. Now, Michael reaction has also found useful application in the synthesis of biomolecule calciamycin, and this is the last reaction you can see. So this is the end for this presentation. I hope you all enjoyed it. I am so grateful to you, to your patience. Thank you all from bottom of my heart. Have a good day.
Thank you so much, Deblina. If there are any question related to this topic, so I request to ask. Okay, I think there is no question, so I continue. Our next participant is Shivam Pal from semester 5, and her topic is classification and use of glasses. So I request Shivam Pal to share her discussion. His.
Shivam speaker on code.
Please unmute.
Shivam, unmute yourself.
Good afternoon, everyone. Myself Shivam Pal in semester 5 of Navadip Vidyasagar College in Department Chemistry, and my topic is classification and uses of glass. Introduction. Now I discuss the introduction of this topic. Glass is an inorganic solid material that is usually transparent or translucent as well as hard, brittle, and impervious to the natural elements. Glass is being used as an engineering material. It is a mixture of metallic silicates, one of which is usually that and alkali metals. Some main properties of the glasses are: glass is solid and hard material. It is disordered and amorphous structure. It is transparent to visible light. It is inert and biological inactive material. And glass is 100% recyclable and of the safest packaging material due to its composition and properties. Classification of glass. Glass is classified mainly in three categories. These three types of glass make up around 95% of the cooled glass used in the production process. These are type 1 neutral or borosilicate glass, type 2 is treated soda lime glass, type 3 soda lime glass. But there are also various type of glass are explained. The first type of glass is neutral or borosilicate glass. Borosilicate glass is produced by replacing the sodium oxide by boric oxide and soda lime by alumina in the basic components of glass. The chemical composition of the glass is SiO 80%, Al2O3 95%, Na2O 7%, K2O 0.5%, B2O2 12%, and CO 1%. These glasses have some properties. Borosilicate glass possesses a high hydrolytic resistance. It is the most inert type of pharmaceutical glass. It has the lowest coefficient of thermal expansion. Use. It is suitable for packing all pharmaceutical preparation. It is widely used as glass ampoules and vials to package fluids for injection. In contrast to other type of glass, this glass has no or little amounts of basic oxides, so it is used to package solution that could dissolve basic oxides in the glass. The next example is treated soda lime glass. This glass is made from commercial soda lime glass that has been dealkalized or treated to remove surface alkali. The dealkalizing process is known as surface treatment. Sulfur treatment neutralizes the alkaline oxide on the surface, rendering the glass more chemically resistant. The composition of the glasses are SiO 80%, Al2O3 95%, Na2O 7%, K2O 0.5%, B2O2 12%, and CO 1%. These glasses this glass has also some properties. This glass has lower melting point than type, that is neutral or borosilicate glass. It is thus easier to produce and consequently cheaper. High hydrolytic resistance due to surface treatment of the glass. Use. This glass is used to package aqueous preparation. However, as it contains basic oxides, it is not used to package parenteral formulation with pH less than 7, that is acidic. This would increase the pH of the formulation and could affect the drug stability and potency. It is the glass used to produce the container for eye preparations and other dropper bottles. The next is soda lime glass. Soda lime glass is usually of soda lime silica glass with only moderate hydrolytic resistance. The composition of soda lime glass is 73% SiO2, 15% Na2O, 7% CaO, 4% MgO, and 1% Al2O3. The properties are about 90% of all glass is soda lime glass made with silica, sand, calcium carbonate, and soda ash. They are low cost, resistant to water, but no acids. They can melt easily and hence can be hot worked. Use. Soda lime glass is used to make window glass, electric bulbs, plate glass, bottles, jars, cheaper tableware, test tubes, and reagent bottles, etc. This glass is acceptable in packaging some dry powders, which are subsequently dissolved to make solutions or buffers. It is also suitable for packaging liquid formulation that prove to be insensitive to alkali. The type 4 or the next example is potassium glass. It is also known as hard glass or Bahamian glass. The composition is the mixture of potassium silicate and calcium silicate. Properties are it does not melt easily, that's why fuses at high temperature, and this glass is used in the manufacture of combustion tube and etc. The next is potash lead glass. This glass, also termed as flint glass, this is a mixture of lead silicate and potassium silicate is the composition of this glass, and the properties is it fuses easily and turns black opaque. Uses this glass is used in the manufacture of lenses, prisms, electric bulbs, artificial gems, and etc. The next is colored glass. To produce colored glass, coloring pigment is added which is obtained from metallic oxides, finely divided metals, carbon salts of metal, sulfur, etc. Properties: different colored glass needs different quantities of same substance. Colored glass used for window panels, fancy articles, decorative articles, and etc. The next is common glass. A common glass that may be yellow, green or brown. Composition is a mixture of sodium silicate, iron silicate and calcium silicate. Properties: it does not fuses easily but attracted by acids easily. This glass used in the manufacture of medicine bottles. The other is laminated glass. When this glass breaks, it does not fly off in splinters. The properties is two or more sheets of glass are attached with plastic design between them. Laminated glass ensures safety at places where glass is liable to shatter. The next is tempered plate glass. This glass is much stronger than ordinary glass. Properties: it made by glass plate which is heated then cooled to temper it immediately. Used in glazed entrance doors, making table, top shelves, counters, etc. And my last example is soluble glass. This glass is soluble in water. Composition: it's made by melting quartz sand, grinding and mixing it with soda ash, sodium sulfate or potassium carbonate. Use: this glass used for making acid resistant cement. Thank you everyone.
Thank you so much. If there are any question related to this topic, so I request to ask. Okay, I think there is no question. So Somnath Parui, semester 5, and his topic is sonochemistry.
Good afternoon, everyone. I am Somnath Padui, studying at Navadip Vidyasagar College, Department of Chemistry. Today, I am going to discuss about a very interesting and useful topics: sonochemistry beyond synthesis. At first, we should know about the definition of sonochemistry. So, what is the sonochemistry?
সোমনাথ ইকো হচ্ছে।
Sonochemistry,
হ্যালো সোমনাথ ইকো হচ্ছে।
হ্যাঁ স্যার।
শিবম দার মাইকটা অন আছে বলে ওকে
শিবমকে মিউট করতে হবে।
হ্যাঁ শিবম একটু মিউট করো তোমার।
স্টার্ট করো, মিউট। স্যার স্টার্ট করব?
করো।
So what is sonochemistry? Sonochemistry, the use of sound energy, that is ultrasound, to induce physical or chemical changes within a medium. Begin with the discovery that simple ultrasonic decaying baths could be used to influence a range of chemical reactions. Now the field has expanded outside of chemical synthesis, like finds application in food industry, medicine, nanoscience, environmental remediations, and also biotechnology. After the definition of ultrasound, we should know the power of ultrasound. Ultrasound is classified as sound beyond the energy that can be detected in by the human ear. The normal range of human hearing is between 16 Hz to 20 kHz, and the ultrasound range is from 20 kHz to 10 MHz. Sometimes it is also called silent sound. After the power of ultrasounds, the next topic is history of sonochemistry. Sir Alfred L. Loomis noticed the first effect of ultrasound in 1927, but the field of sonochemistry lay fallow nearly for 60 years. Biologists much more concerned with the effect of ultrasound on bacteria, viruses, and other microorganisms. Here the picture of Sir Alfred L. Loomis. Next, sonochemical formation of ultrasound assisted chemistry. In chemistry, the study of sonochemistry is concerned with understanding the effect of ultrasound in forming acoustic cavitations in liquids, which enhanced the activities of chemical reactions and compared to the normal reactions. Sonochemistry not only used for chemical synthesis, but also it is used beyond the chemical synthesis, including the diagnostic medicines, ultrasound physiotherapy, one of them. Using the high frequency ultrasound at low power is now a routine procedure at diagnostic medicines. Such frequencies and low energy of ultrasonic waves cause no permanent effect on tissue as passed through the body. This is the treatment of ultrasonic physiotherapy. An important feature of ultrasound is that it can penetrate in the human body. Ultrasound energy can be used on our malignant side to read deep in tissue, and this type of therapeutic ultrasounds has two applications. One of these is sonodynamic therapy. So what is it? In this treatment, a patient is given a chemotherapeutic drug which accumulates in cancerous tissue and is activated by focused ultrasound. A possible mechanism for this is the sonochemical formations of radicals which initiate chain peroxidations of membrane lipids via peroxy or alkoxy radicals. Here the mechanism of lipid peroxidations where polyunsaturated lipid forms lipid peroxy radicals through chain initiations. And the second applications involves the use of a more powerful array that generates such a concentrations of energy that the tumor cell can be killed with sound. This is known as high intensity focused ultrasound. Applications of ultrasound in pregnancy. Applications of ultrasound in pregnancy is the most useful applications in diagnostic medicines such as medical field. An ultrasound can provide very important diagnostic information about a developing baby, including confirming the pregnancy and gestational age, checking for multiple pregnancies and problem with placenta, and also check the fetal heartbeats, fluid, etc. Recommended ultrasound schedule for pregnant women. Ultrasound help us to confirm pregnancy at 7 weeks and know about molar pregnancy, which is a non-cancerous tumor that develops in the uterus as a result of a non-viable pregnancy. Also determine due date. At 13 to 14 weeks, evaluate possibility of Down syndrome, and at 18 to 20 weeks detect other anomalies and evaluate size, verify placental position at 34 weeks. Here the picture of ultrasound. And the next applications of sonochemistry is food technology and food preservations. One of the success stories of modern chemistry has been the evolution of a system that is increasingly more efficient at directly translating knowledge into technology and commercial products. Food products such as fruit and vegetables, fat and oils, sugar, dairy, meat, coffee and cocoa, and other organic and mineral compounds. Ultrasound in food processing. The first application is filtrations. In the food industry, the separation of solids from liquids is an important procedure either for the production of solid-free liquor to produce a solid isolated from its mother liquor. And the second application is defoaming. Foam is a dispersion of gas in liquid with a density approaching that of the gas, that is, in which the distance between individual bubbles are very small. Foam find applications in a wide range of industrial processes, including food productions and cosmetic. And number three applications is cutting. The introductions of ultrasound in food cutting has improved the performance of overall food processing. Ultrasonic food cutting equipments provide a new way to cut a slice or a variety of food products that streamlines productions, minimize product wastes, and lowers the maintenance cost. Here the picture of cutting slices of a bakery product cut with and without ultrasounds. And next applications is depolymerizations. This is the one of the oldest applications of ultrasounds is the degradations of polymers. That the polymerization process occurs through the effects of cavitations and can involve two possible mechanisms: mechanical degradations of the polymer from collapsed cavitations bubbled and chemical degradations. Here the representations of depolymerization phenomena using ultrasound. And the last applications of food processing is drying. Acoustically assisted drying has been a topic of interest for many years. High temperature damage the food, which in certain cases may change the color or taste and also change the nutritional value of the rehydrated product. Alternative process is ultrasonic assisted air drying, now appearing in the design of fluidized bed type systems. The fluidized bed reactor is a vertical cylindrical metal tube driven in a radical at 21.8 kHz with hot air passing through small pieces of carrot cubes and lemon peel cylinders. Nanotechnology and nanosize is a huge application of sonochemistry. Sonochemistry is also used to prepare nano-sized compounds. The approach was pioneered in the early 1990s by Ken Saslik and his co-workers, who sonicated FeCO5 either as a neat liquid or in a decalin solutions and obtained 10 to 20 nanometer size amorphous iron nanoparticle. Many different methods using sonochemistry is the synthesis of nanomaterials have now been developed. One of the more recent applications is the formation of proteinaceous micro and nanospheres. Extractions of natural medicines. The compounds in recent years, the renewed interest of drug companies in the active constituents of natural remedies as leads for new synthetic drugs from plants. Sonochemistry has been found to increase efficiency and shorten extraction time for a range of plant-derived compounds. The compounds in the flowers, leaves, and stems of sage, the scientific name of sage is Salvia officinalis, have a wide spectral antimicrobiological activities. Extracts are used to cure and prevent inflammations in the mouth, skin, disease, and sometimes stomach inflammations. This is the picture of sage. Using aqueous ethanol as solvents, the extractions of active compound from sage, including cyanol, thuzone, and borneol, can be increased by more than 20% using sonochemistry compared to normal extractions condition. This is the picture of cyanol, alpha thuzone, beta thuzone, and the last one is borneol. A quiet revolution. Sonochemistry has come a long way from its origins in chemical synthesis, helped over recent years by the increased availability of inexpensive and reliable ultrasonic apparatus. Today, the subject has a multidisciplinary approach with chemists, physicists, biologists, and medics working together to identify new opportunities beyond pure chemistry. with proven new applications in medicines and environmental remediations. Industry and academia are turning to ultrasound technology to develop more effective and efficient processes. Sonochemistry is said to provide a quite revolution in modern science. Thank you.
Thank you so much. If there are any question related this topic, so I request to ask. Okay, I think there is no question.
আচ্ছা আচ্ছা
So,
নীলাঞ্জনা একটু একটু আমি প্রিন্সিপাল এসছেন একটু কথা বলছি স্যার আপনি
yes,
আছেন স্যার
স্যার ছিলেন এখন না দেখতে পাচ্ছি না
আমার মনে হয় এখন আর দেখতে পাচ্ছি না
মনে হয় লিভ করে গেছেন
হ্যাঁ হ্যাঁ
উনি এসেছিলেন মনে হয় লিভ করে গেছেন নেটওয়ার্ক প্রবলেম বা যে কোনো কারণে
ঠিক আছে তাহলে
ঠিক আছে আমরা কন্টিনিউ হোক পরে যদি আবার উনি জয়েন করেন
আচ্ছা ঠিক আছে ঠিক আছে কন্টিনিউ
okay, ma'am. Our next participant, Shreya Dev from semester 3, and her topic is conductometric titration. Please, Shreya.
Am I audible to you all?
Yes.
Yes.
Hello.
শোনা যাচ্ছে
Let me share my screen. Okay, let me share my screen first.
হ্যাঁ শোনা যাচ্ছে
Is it to you all? Hello.
yes it's visible
Yes.
you can continue yes it's visible
Okay, firstly, good afternoon to all my respected Before I started, I would like to thank all to be in front of you all. And special thanks to Shoma ma'am who helps me to acquire more knowledge about this topic and guide me to deliver the presentation well. So today my topic is conductometric titration. In real life, we are very curious to know the concentration of unknown solutions. Yes, it is conductometric titration. Actually, is a measurement point titration measuring conductance. Now, how can you measure the conductance? Okay, this is not a big issue. You can measure it by the help of conductometer. Here you can see the picture. Now you can determine equivalence point by doing acid-base titration also. So now the question arises, then why we need to study conductance? Okay, let me explain it. In acid-base titration, we measure how much acid or base is present in solution by determining the equivalence point of the reaction. Recognize the equivalence point by the help of indicator, which turns to a vivid color once the equivalence point has been reached. Now, this is difficult to determine the equivalence point because we have to keep our eyes in level with the liquid surface while taking the burette reading, and also have to take care that there is no leakage from the burette during titration because it can destroy our burette reading. This titration, that this is a human control process and we have to observe it naked. Now, these drawbacks can be overcome by the point is being determined graphically. Is important role reciprocal of resistance. In simple way, it is conducting power or the readiness with which a conductor transmits an electric current. Now there is two types of conduction. One is metallic and the another one is electrolytic. Now I am not detailed explanation of metallic conduction, but we have to understand electrolytic conduction. Here in a beaker we take acid to a battery. The negatively charged electrode is called cathode, where reduction occurs, and the positively charged electrode is called anode, where oxidation takes part. As the electrolyte dissociates to form cation and anion, they get attracted toward the oppositely charged electrode. Since in anode, the electron which is released by oxidation flow from the anode to cathode through the external circuit, generation of an electrical current occurs on the opposite direction of the electron flow. Now, many factors affect conductance, but I will discuss some particular points which will help us further to understand conductometric titration. Now, first one is number of ions. With increase in the number of ions, conductance increases. And now there is two types of electrodes. One is strong and the another one is weak. Since strong electrolytes ionizes almost completely in the solution, it shows high conductance. Second factor is size of ions. With increase in the size of ions, speed or you can say mobility decreases. So the next point is solvent. With the use of solvent, then an unexpected increase in the mobility of that ion. This phenomenon was first proposed in 1806 by T. Grothus. According to this mechanism, the excess proton hops between water excessive covalent bond formation and breaking events. Here you can see the picture to understand it better. Now, as I already gave a detailed explanation of conductance, now this leads me to the most important segment of my conductometric. Now, note that conductometric titration not only used for acid-base titration, it is similarly reaction, precipitation reaction, and complex formation reaction also. As we are very much familiar in our practical life with the acid-base titration, so here I will discuss about the various types of acid-base titration only. There is four types of acid-base titration: strong acid versus weak base, and weak acid versus weak base. First one is strong acid versus strong base. Now here we take strong acid, let's say HCl as an analyte. Now note that water in beaker is called analyte because we are analyzing the solution throughout the process. And take strong base, let's say NaOH as a titrant, which we take in burette. Now, initially the conductance is high because we know HCl is a strong acid. So it will completely dissociate into H plus and now completely this H minus ion will combine with the H plus ion of HCl to form undissociated water. Show conduction. Plus combine to H minus ion to form water molecules. Now in solution, H plus and Cl minus ions are left, which means all the solvent accelerated H plus ions are, which results in the gradual increase point. At this point, the conductance reaches the minimum value. Now, if we further add NaOH, which will dissociate to form Na plus and OH minus ions, result in the increase in number of ions, as well as the net mobility of the solution increases due to solvent accelerated OH minus ions. So, a sharp increase in the conductance observed. Here you can see the graph of conductance versus the volume of base added in the solution. Next one is weak acid versus strong base. Here we take the weak acid, let's say acetic acid, in the beaker and strong base NaOH in the burette. Initially, conductance is low due to low ionizing power of acetic acid. It dissociates very feebly to form acetate ion and H+. Now, if we add the strong base NaOH in the solution, the H- ion will combine with the H+ to form undissociated water molecule. As a result, in the solution, concentration of H+ decreases. Now we all know, according to La Chatelier principle, if the concentration of the product decreases, then the equilibrium shifts to forward direction. So more number of acetic acid will dissociate to form more number of H+ ions. Now on successive addition of NaOH, all the H+ ion will neutralize by H- ions. Actually, here the weak acid starts to act like strong acid, as it completely dissociates to increase the concentration of H+. So the conductance will increase gradually till the equivalence point. Now if we further add NaOH, number of ion as well as the solvent accelerated ion Next one is strong acid versus weak base. We take strong acid in a beaker, for example HCl, and weak base NH4OH in a burette. Initially, conductance is high due to high ionizing power of HCl. On successive addition of NH4OH ion replaced by NH, so the mobility decreases and so the conductance decreases gradually. At equivalence point, conductance reaches the minimum value as all the H+ ions are replaced by Na+ ions. Now in the solution, there is only Na+, NH4+, and Cl- ions are present. Now if we further add NH4OH in the solution, as NH4OH is a weak base, it will almost exist in the solution in its undissociated form. Due to the common ion effect of NH4+, the dissociation of excess NH4 is suppressed. So beyond the equivalence point, conductance virtually remains same. The weak base which is being added is feebly ionized. Here is the graph. Last one is weak acid. The curve before the equilibrium point, equivalence point is similar to the thing by subtracting weak acid for at the equivalent point, conductance virtually remains same as the weak base which is being added is feebly ionized. Therefore, is not much conducting. So, if now I summarize my presentation, I will say is a very important method accurately without any help. And it is in case of this leaves me at the end of my presentation. Thanks to all for listening me today, this evening. Thank you.
Thank you. If there any question related this topic, so I request to ask. Okay, I think there is no question. The rest part of the seminar will be continued by my friend Deblina Datto. Please, Deblina, I request you to continue this seminar.
Our next participant is Nobonita Chakraborty from semester 5 and her topic is Role of Green Chemistry in Controlling Environmental Pollution. Please share your screen.
Hello everyone, good afternoon. I am Nabonita Chakraborty, student of Navadip Vidyasagar College, Department of Chemistry, 5th semester. Now I am going to start my presentation on the role of green chemistry in controlling environmental pollution. Introduction. The United States Environmental Law The Pollution Prevention Act of 1990 stated that the first choice for preventing pollution is to design industrial processes that do not lead to production of waste. This made the methodology for green chemistry as the design of chemical products and processes that reduce the use of hazardous substances. Environmental chemistry is the chemistry of natural environment and of pollutant chemicals in nature, whereas green chemistry particularly tends to reduce and prevent pollution at source. Basic principles of green chemistry. There are 12 basic principles of green chemistry. Prevention, less hazardous chemical synthesis, reduced derivatives, atom economy, designing safer chemicals, solvents and auxiliaries, design for energy efficiency, catalysis, design for degradation, real-time pollution, prevention, use of renewable feedstocks, and safer chemistry for accident protection. Next, pollution prevention hierarchy. Pollution prevention is efforts that reduce or eliminate the toxicity of waste. The Pollution Prevention Act of 1990 set up a hierarchy of preferred approaches to protecting the environment. First and foremost, pollution should be prevented at the source whenever feasible. If waste streams cannot be prevented, they should be reused, recycled, or treated. Disposal should be the last resort. Green chemistry is the use of chemistry for pollution prevention. Green chemistry is an approach for addressing the environmental consequences of products and processes at the design stage. It is a new and straightforward method defined as the design of chemical products and processes that reduce the use and generation of hazardous substances. Minimize waste. This approach to the problem has brought positive results. The paint and varnish industry already produces solvent-free paints and lacquers. The detractors industry has already thrown out all phosphorus-containing detergents. Asbestos is no longer used in practice. Next synthesis, green synthesis of acetylene. Green synthesis of acetylene, by which the introduction of ethanol as the sole solvent eliminates the need for the use, distillation, and recovery of four solvents such as methylene chloride, tetrahydrofuran, toluene, hexane, resulting in a reduction in solvent consumption of 250 to 25 liters per kg of acetylene. And there is the green synthesis method of acetylene. Next, environmental and health hazards of adipic acid synthesis. Number 1. Benzene is a volatile organic compound and its inhalation can lead to leukemia and cancer. Number 2. Moreover, benzene is a byproduct of petroleum manufacture and it is produced then from a non-renewable source. Number 3. The last step in the current manufacture of adipic acid involves oxidation by nitric acid, which results in the formation of N2 that is released into the atmosphere. It is factor in the destruction of ozone layer. It is also acts as greenhouse gas. And there is industrial synthesis of adipic acid. Next, green synthesis of adipic acid. In green synthesis of adipic acid, the starting material is glucose, and glucose itself derives from renewable carbohydrates feedstocks such as starch cellulose. In addition, water is used as primary reaction solvent, thereby avoiding the generation of toxic intermediates and environmental damaging byproducts. Glucose is transformed into hydroquinone catechol C6-meconic acid by means of a genetically engineered microbe in a novel biosynthesis pathway which was assembled using recombinant DNA technology. And you can see there is gene synthesis method of adipic acid. Let's see designing effective non-toxic products to prevent the pollution. Tributyl tinoxide and 4,5-dichloro-2N-octyl 4-isothiazoleic 3,1. Both are antifouling agents, but former is degraded very slowly, but second one is rapidly, though both are toxic to the marine organism. And you can see the structure of tributyl tinoxide and 4,5-dichloro-2N-octyl 4-isothiazoline 3,1. Fouling is the unwanted growth of slime grasses on a ship's surface, and this causes huge cost in the shipping industry. A significant portion of this expenditure derives from the increased fuel consumption needed to overcome the ensuing hydrodynamic drag. Besides, increased fuel consumption also contributes to pollution, global warming, etc. Design good synthesis. Synthesis of polycarbonate. The family of polycarbonate contains very important polymers which are used where high optical properties combined with strength are needed. The polycarbonate most used in manufacture from bisphenol A. The polycarbonate is manufactured by a condensation reaction between bisphenol A and carbonyl chloride or diphenyl carbonate. Carbonyl chloride is a very poisonous gas manufactured from other hazardous gases, carbon monoxide and chlorine. An alternative procedure. On the other hand, diphenyl carbonate is produced from dimethyl carbonate, which is readily manufactured from methanol, carbon monoxide and oxygen in the liquid phase in presence of CuCl2. And there is the reaction to form dimethyl carbonate. Dimethyl carbonate, when heated with phenol in liquid phase, forms the diphenyl carbonate. And there is the reaction. Let's see how green chemistry controls environmental pollution by using a variety of green alternatives to conventional methods. Organic synthesis in water. Although water is considered a problem for organic synthesis and the purification process, yet in recent years water is considered as good solvent for organic reaction. In Diels-Alder reaction, water is used as ideal solvent. Use of sulfur chemicals to prevent pollution. We use solvents regularly in our daily lives and in the chemistry laboratory. Widely used solvents in synthesis are toxic and volatile alcohol, benzene, etc., which add to pollution and can be highly hazardous to human health. The development of green chemistry redefines the role of a solvent. An ideal solvent should be natural, non-toxic. Green quantitative analysis using flower petals extract as indicator. The synthetic indicators like phenolphthalein, methyl orange are not only hazardous to health but are also prominent pollutants. The green chemistry has proved that these unsafe chemicals can be substituted by the petal extract as an indicator for acid-base titration, which are neither harmful to the environment nor it causes any health hazards. Chemists are also trying to find more environmental friendly and sustainable methods to be used in daily life. Some examples are discussed below. Eco-friendly paints. Oil-based alkyd paints give up large amounts of volatile organic compound as it dries and cures. These volatile organic compounds have many conventional environmental effects. A mixture of soya oil and sugar is established to be used in place of petroleum petrochemicals, derived paints, resins and solvents which reduce the hazardous volatile by 50%. Green bleaching agent. Conventionally, during manufacturing of good quality of white paper, lignin from wood used for it is removed by placing small pieces of wood into bath of sodium hydroxide and sodium sulfide, followed by its reaction with chlorine. In this reaction, chlorinated dioxins and chlorinated furans are formed. These compounds, being carcinogens, cause health problems. Terence Collins of Carnegie Mellon University developed a green bleaching agent which breaks down lignin in a shorter time and much lower temperature. Conclusion: though many exciting green chemical processes are being developed, but there are far greater challenges lies ahead. The greatest challenge is to incorporate the green chemistry in industrial laboratory and day-to-day processes in order to control environmental pollution at source. This can be achieved by training and educating new generation of chemists. Green chemistry has been introduced in our syllabus to make us aware in our life. Thank you everyone.
Thank you, Nabonita. Now you can stop your presentation. And is there any question? I think there is no question. So our next participant is Bitande from semester 3, and his topic is hydrogen bonding and its application. Bitan, you can share your screen.
স্যার দেখা যাচ্ছে?
Yes.
স্যার দেখা যাচ্ছে?
হ্যাঁ দেখা যাচ্ছে।
Good
দেখা
afternoon.
যাচ্ছে।
Good afternoon, everybody. I would like to thank to organize for giving me chance to participate in this seminar. I am Bitande, third semester student of Chemistry Department of Navodip Vidyasagar College. Today I am here to represent my views about the topic hydrogen bonding and its application. Hydrogen bonding. When hydrogen is bonded to a highly electronegative atom such as nitrogen, oxygen, and fluorine, the bonding electron pairs is drawn towards the electronegative atoms. Hydrogen has no inner shell electron and is very small size. The positive charge density develops is high. The nucleus of hydrogen atom is exposed to attraction by nearby electron clouds, a lone pair electrons of the electronegative atom. Now we have to discuss about the definition of hydrogen bonding. Now the definition is electrostatic attraction between hydrogen atoms bonded to small, strongly electronegative atoms such as nitrogen, oxygen, and fluorine, and the lone pair electrons on this electronegative atom. Here we shown hydrogen bonding in this picture. Next, the essential requirements are: number 1, the hydrogen atom must be directly bonded to a highly electronegative atom. Example, fluorine, oxygen, and nitrogen. Number 2, an unbonded pair of electrons is presented of the electronegative atoms. Now some example of hydrogen bonding are represented here. The hydrogen bond have seen. Number 1, hydrogen fluoride. Number 2, water. Number 3, ammonia. And number 4, methanol. Now we have to know some special note about hydrogen bonding as intermolecular hydrogen bond and intermolecular hydrogen bond, which is very important in hydrogen bonding. Intermolecular hydrogen bond, when hydrogen bond formed between two molecules. And intramolecular hydrogen bond formed between two different atoms in the same molecules. We have to note that intermolecular hydrogen bond is strong than van der Waals force. we represented in physical phenomena how important is hydrogen bonding. We have to consider anomalous property of the second period hydrides. Now from this why, the explanation of this question is, why do you H2O, NH3 and HF have abnormally high boiling point? The explanation is, number one, nitrogen and oxygen are highly electronegative atom forms intermolecular hydrogen bonds in their hydrides. Intermolecular hydrogen bonds are much stronger than van der Waals force. So in the case of NH3, H2O, HF, the bond are very, very strong intermolecular hydrogen bond. So break hydrogen bonding, this type of bond, we have to needed more energy. So boiling point NH3, H2O and HF is abnormally high. Now we describe dimerization, boiling point and solubility of alcohols. The boiling point of alcohols are higher than thiols because there are intermolecular hydrogen bonds between alcohol molecules, but only dipole-dipole interaction between molecules of thiols. Alcohols of low molecular masses are soluble in water because they can form intermolecular hydrogen bond with water molecules. Importance of hydrogen bonding in physical phenomena. Dimerization of carboxylic acid. It happens when carboxylic acid are dissolved in non-polar solvent or in vapor state. Example, ethanoic acid. Ethanoic acid molecules form dimers, though the formation of intermolecular hydrogen bonds. Next, importance of hydrogen bonding in biochemistry. Hydrogen bonding in ice and water. Intermolecular hydrogen bond exists in both water and ice. In water, molecules are constant motion. Intermolecular hydrogen bonds are formed and broken constantly. The arrangement of molecular is random. In ice, the molecular motion is restricted. The molecules are arranged in a way from the maximum number of hydrogen bonds. Each H2O molecules is tetrahedrally bonded to 4 other H2O molecules by hydrogen atoms, creates an open structure and give rise to a lower density of ice than water. Insolates the water below and prevents complete solidification. Keep fish survive in polar region. Now we discuss about the hydrogen bonding in DNA. Hydrogen bonding in DNA. Structure of DNA. The building block of DNA nucleotide. Nucleotide, a sugar, a phosphoric acid unit, a nitrogen containing heterocyclic base, adenine, thymine, cytosine, and guanine. The two nucleic acid chains are held together by hydrogen bonds that are formed between specific pairs of bases on the chains. Hydrogen bond of base pairs in DNA, adenine, thymine, cytosine, guanine. So that's all. Thank you.
Thank you, Bitan. Is there any question? Okay, I think there is no question. So our next participant is Nilanjana Das from semester 3 and her topic is asymmetric hydrogenation, a novel reaction for drug and synthesis.
Is it visible?
Yes.
Good afternoon, everybody. Myself, Nilanjana Dash, third semester in Chemistry Honors of Navadip Vidyasagar College. First of all, I would like to pay my heartiest respect to all the respected persons who are present here and my best wishes of all my friends. Today, my topic is asymmetric hydrogenation, a novel reaction for drug synthesis. Well, today we know the importance of chemistry in our daily life. The ultra modern achievements of science have brought our civilization to the pinnacle of progress. Like other branches of science, medical science is also very relevant. Medicine is inextricably linked with our daily life. We take many types of medicines in our life. One of the most valuable and famous medicine is L-Dopa. Now I say about L-Dopa. L-Dopa is known as levodopa. It is an amino acid, L,3,4-dihydroxyphenylalanine, that is made and used as part of normal biology of human as well as some animals. It is the precursor to the neurotransmitter dopamine, norepinephrine, and epinephrine. It is used as a psychoactive drug for the treatment of Parkinson's disease. This is the structure of L-Dopa. From the normal hydrogenation, we can't get this product. Right now, I think a question on your mind that how will we prepare this product? This answer we get in 1956. A heterogeneous catalyst made of palladium deposited on silk was shown to affect asymmetric hydrogenation. In 1968, William Knockles and Leopold Honor independently published the example of asymmetric hydrogenation using a homogeneous catalyst. Here is William Knockles and Leopold Honor. The importance of asymmetric hydrogenation was recognized by 2001 Nobel Prize. Yes, Nobel Prize in Chemistry awarded William Shannon Knockles and Rosinori. Rosinori is Japanese chemist. He is most famous for asymmetric hydrogenation using as catalyst complex of rhodium. In 1972, the antibacterial agent levofloxacin is manufactured by asymmetric hydrogenation of ketones using presence of rhodium binap by Nuri. Here is William Shannon Knockles and this is Roginari and this is the Nobel Prize. To proceed the reaction, a symmetric hydrogenation, specific catalyst we used rhodium-based catalyst and palladium-based catalyst. This is the proposed mechanism of asymmetric hydrogenation. Here we take an unsaturated compound, then we apply rhodium catalyst and we get desired product. It is a proposed mechanism. Rhodium. Rhodium is not only on the first metal but also one of the most efficient ones. It is very rare. This is the structure of rhodium catalyst and here is palladium based catalyst. By using this catalyst in the reaction, we get asymmetric hydrogenation of dihydroamino acids, highly enantioselective. Here is the reaction of hydration of dihydroamino acids. This double bond reduced here. Here is the asymmetric hydrogenation occur. This is the enantioselective product S,2,6-dimethyl tyrosine. From this reaction, we get many types of medicines. At the starting of my speech, I said about L-Dopa. This is the most important application of asymmetric hydrogenation. L-Dopa. It is used in the clinical treatment of Parkinson's disease and dopamine responsive dystonia. This is the structure of L-Dopa. Here, this double bond is reduced in presence of hydrogen and rhodium catalyst. This is our desired product. Another one is levofloxacin. Levofloxacin is antibiotic. It is used to treat a number of bacterial infections, pneumonia, sinusitis, urinary tract infections, chronic prostatitis, and some types of gastroenteritis. This is the starting materials to This is the levofloxacin. Here, this carbonyl bond reduces in presence of hydrogen and rhodium binap catalyst. This is a colorful molecular structure of levofloxacin. Carbapenem is also very effective and famous medicine. Carbapenem, a class of highly effective antibiotic agents. Commonly, it is used for the treatment of several or high-risk bacterial infections. Those are beta-lactam derivatives. This is the starting compound. Here, this carbonyl group and this double bond both are reduced in presence of hydrogen and rhodium catalyst. This is the final structure of carbapenem. Here is BMS181100 is known as BMY14802 is a drug with antiseptic effects. This is the starting materials, and here this carbonyl bond is reduced here. Here asymmetric hydrogenation occur. This is our desired product in structure of VMS181100. Nowadays, heart problem is very common. So, the Ramipril is used for heart treatment. Ramipril is used to treat high blood pressure, to lowering the blood pressure, helps to prevent strokes, heart attacks, and kidney problems. It may also be used in high-risk patients such as diabetes. This is the starting materials to formation Ramipril. Here, this double bond is reduced in presence of hydrogen and rhodium catalyst. This is our desired product. It is the structure of Ramipril. Sitagliptin. Sitagliptin is used with a proper diet and exercise to control high blood sugar, prevent kidney problems, blindness, nerve problems. This is the starting material to formation sitagliptin. Here this double bond reduced. Here a symmetric hydrogenation occur. This is the structure of sitagliptin. It is a colorful molecular structure. This medicine impossible to make without asymmetric hydrogenation. So, asymmetric hydrogenation plays an important role for production of these medicines. So, we may hope that the coming days, asymmetric hydrogenation will help us more prosperities of medical science. So, it is my pleasure to share my words with everyone. I hope that you will have a very happy and healthy life. With this hope, goodbye and thanks to all.
Thank you, Nilanjana. Now you can mute yourself. So, our next participant is Joyashree Mollik from semester 3, and her topic is Furjan's rule. Joyashree, please share your screen. Joyashree, your volume is very low.
Just unmute yourself.
ওকে কেউ ফোন করে বলো।
মিউট করা আছে, শোনা যাচ্ছে না।
হ্যাঁ সেই তো মিউট করা আছে।
স্যার ও আনমিউট আছে দেখাচ্ছে কিন্তু ওর ভলিউম আসছে না।
ও তাহলে একটু ফোন করে বলা যায় না?
না
শোনা যাচ্ছে না তো কিছু।
অ্যাকচুয়ালি এক্সিট করে আবার জয়েন করলে হয়তো
ও
দেখতে হবে।
আচ্ছা আচ্ছা।
প্রেজেন্টেশনটা অফ করে আরেকবার দেখলে হয়তো কাজ হবে।
Joyce, I think there's a problem in your headphone. Just remove it and let it speaker.
স্যার এখন শোনা যাচ্ছে?
Yeah. Now continue.
হ্যাঁ শোনা
শোনা
যাচ্ছে।
যাচ্ছে।
তাহলে স্যার আমি ফার্স্ট থেকে শুরু করি এখন।
হ্যাঁ তুমি স্টার্ট করো, প্রেজেন্টেশন দিয়ে স্টার্ট করো।
Good afternoon, everyone. I am Joyashree Mollik, third semester student of Navodip Vidyasagar College. First of all, I would like to thank our teachers for giving me this opportunity of this seminar. Today, I am here to represent my presentation about Furjan's rule. So let's start. So what is Furjan's rule? Furjan's rule predicts whether a chemical bond will be ionic or covalent, which depend on the charge of the cation and relative size of the cation and anion. In 1923, scientist Kazimierz Furjan discussed about the rule that few ionic bonds have partial covalent characteristics. In the time, with the help of X-ray crystallography, he was able to predict ionic or covalent bonding with the attributes like ionic and atomic radius. With this content, we explain the total Furjan's rule. The contents are postulate, explanation, detailed illustration, example, and summary. What is Furjan's rule? We classify certain compounds as ionic and other compounds as covalent. Now, if we were to ask amongst the alkali chlorides which is the most ionic, so to answer this type of question, we employ Furjan's rule. To understand the Furjan's rule, let us first understand some few terms. To explain Furjan's rule, we have to explain the factors polarizing power and polarizability. Polarizing power is the factor of a cation. It is the extent to which a cation can polarize an anion. It is proportional to charge density. Charge density is the ratio of charge to volume. More the charge density, greater is the polarizing power for the cation. Now we discuss polarizability. It is the extent to which an ion can be polarized. It can also be called as the ease with the which an ion can be polarized. Polarization is the distortion of a spherically symmetric electron cloud to an unsymmetric cloud. Now we discuss some postulates of Furjan's rule. The rule can be stated on the basis of three factors, which are size of the ion, the charge of cation, and electronic configuration. In the case of size of the ion, smaller the size of the cation, the larger the size of the anion, and greater is the covalent character of the ionic bond. In the charge of the cation, greater the charge of the cation, greater is the covalent character of the ionic bond. Now we discuss the vital part, electronic configuration. For cations with same charge and size, with configuration n-1 d in n0, which is found in transition element, have greater covalent character than the cation with ns to np6 electronic configuration, which is commonly found in alkali or alkaline earth metals. Now, the explanation of Furjan's rule. Rule number 1. The first rule speaks about the polarizing power of the cation. If the cation is smaller, then we can say that the volume of the ion is less. If the volume is less, we can conclude that the charge density of the ion would be high. Since the charge density is high, the polarizing power of the ion would be high. This makes the compound to be more covalent. Now it will be explained by an example. In the case of Na plus and Al3 plus, the radius of Na plus is 96 picometer and the radius of Al3 plus is 51 picometer. Because of the higher charge density in Al3 plus, the size of the Al3 plus is small than Na plus. So polarizing power increases from Na plus to Al3 plus, thus make the ion more covalent. Now, rule number 2. The second rule speaks about the polarizability of the anion. Larger the anion, less is the effective nuclear charge that holds the valence electron of the ion in place. Since the last electron is loosely bound in large anions, it can easily be polarized by a cation, thereby making the compound more covalent. Now it also will be explained by an example. In the case of halide ions, from F minus to Br minus, the size increases as the effective nuclear charge that holds the valence electron of the ion in place also less. So the polarizability increases from F minus to Br minus, as in the compound, the covalent character increases. Now the vital rule, rule number 3. The third rule is a special case. Let us use an example to explain this point. If we want to find the more covalent compound among HgCl2 and calcium chloride, we cannot use size as a factor to conclude. This is because both Hg2 plus and Ca2 plus are of the most equal of size. To explain this, we employ the third rule. The electronic configuration of Hg2 plus is 6s05d10. This configuration is called pseudo-octet because d orbital is fully filled, but the element does not have 8 electrons or an octet. We know that d orbitals are not good at shielding, so we can say that the anion Cl- would be more polarized because the d orbital is poor at shielding, making HgCl2 more covalent than CaCl2 because Ca2 plus ion has a noble gas configuration. Now, to answer the question that we asked first, amongst the alkali chlorides, which one is most covalent? From Furjan's rule, we can explain this. Since the anion is the same, we have to compare the cations. According to Furjan's rule, smaller the cation, more is the covalency. Therefore, lithium chloride is the most covalent compound. In the Furjan's rule, ionic potential is also a vital part. Cartilage observed that polarizing power is directly proportional to the charge and inversely proportional to the radius of the ion. Then he defined the ionic potential as cation charge and the cation radius ratio. Larger the value of ionic potential for a cation indicates greater polarizing power and hence greater covalent character in a compound. From this, we have concluded that metal ion having root phi less than 2.2 are usually ionic and metal ions having greater than 2.2 are non-ionic. Let us understand Furjan's rule using a detailed illustration. Consider aluminum iodide. This is an ionic bond which was formed by transfer of electrons. The iodine being bigger as the laser effective nuclear charge. Thus, the bonding electrons are attracted laser towards the iodine nucleus. So, on the contrary, the aluminum having 3 positive charges attracts the shared pair of electrons towards itself. This leads to insufficient charge separation for it to be ionic, and so it results in the development of covalent character in aluminum iodide. Now we discuss about some examples of Furjan's rule. Illustration 1. Which compound should theoretically be the most ionic and the most covalent among the metal halides? Now the solution is the smallest metal ion and the largest anion should technically be the most covalent. Therefore, lithium iodide is the most covalent compound. The largest cation and the smallest anion should be the most ionic. Therefore, cesium fluoride should be the most ionic. Now, illustration 2. Arrange the following according to the increasing order of covalency: sodium fluoride, sodium chloride, sodium bromide, and sodium iodide. To solve this question, we have to use Furjan's rule. Since the cation is the same, compare the anions. Amongst the anion, larger the size, more would be the covalency. Therefore, the order will be sodium fluoride is less than sodium chloride, less than sodium bromide, less than sodium iodide. In the case of lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, and cesium fluoride, here the anion is the same. So we compare with cations. Smaller the cation, more is the covalency. Therefore, the order is cesium fluoride is less than rubidium fluoride, less than potassium fluoride, less than sodium fluoride, and less than lithium fluoride. Now, the total Furjan's rule can be summarized as: larger the size of the cation, the ionic characteristic increases, and smaller the cation, covalent character increases. In the case of anion, smaller the anion, the compound will be ionic, and larger the anion, the compound will be covalent. In the case of charge, small charge increases the ionic character, and high charge increases the covalent character. Conclusion. By Furjan's rule, we can speak about polarizing power of cation and polarizability of anion, which help us to know about the covalent and ionic character of the variable compounds. So that's all for today. Thank you, everyone.
Thank you, Jayashree. Now you can mute yourself. So is there any question about this topic? Okay, I think there is no question. So our next participant is Sharnabha Mondol from semester 3, and this topic is differentiation between real gas and ideal gas. Sharnabha, you can share your screen.
Hello everyone. I am Sharnabha Mondol, a student of Navadip Vidyasagar College for first semester. My topic is difference in between ideal gas and real gases. Introduction. An ideal gas is a theoretical gas composed of many randomly moving point particles that are not subject to interparticle interactions. Under various conditions of temperature and pressures, many real gases behaves qualitatively like an ideal gas, where the gas molecules play the role of the ideal gas particles. Next, difference between ideal gases and real gases. The three states are matter that are recognized by their characteristics are solids, liquids, and gases. Solids have definite mass due to the strong molecular attractions. In liquids, the molecules are moving, so they results in taking the shape of the container. In gases, the molecules are free to move anywhere in the container. Two types of gas exist, real gas and ideal gas. As the particle size of an ideal gas is extremely small and thus mass almost zero. The negligible volume ideal gas is also considered as a point mass. The molecules of real gas occupy space through they are small particles and also have volume. Ideal gas. An ideal gas has defined as a gas that obeys gas law at all conditions of pressure and temperature. Ideal gas have velocity and mass. When compared to the total volume of the gas, the volume occupied by the gas is negligible. It does not condense and does not have triple point. Real gas. A real gas is defined as a gas does not obey gas laws at all standard pressure and temperature conditions. When the gas becomes massive and voluminous, it deviates from its ideal behavior. Real gas have velocity, volume and mass. When they are cooled to their boiling point, they liquefy. When compared to the total volume of the gas, the volume occupied by the gas is not negligible. Ideal gas. Ideal gas obey PV equal to nRT equation at all temperature. Behavior of ideal gas is much simpler. Ideal gas has negligible volume and also has point mass. Collisions of ideal gas particles is elastic. No energy involved during collisions of particles in ideal gas. Next comes real gas. PV does not equal to nRT. Real gas obey PV equal to nRT at low pressure and high temperature. The behavior of real gas is very much complex. Real gas has definite volume and mass. Collisions of real gas particles is not elastic. Collisions of particles in real gas has intermolecular force of attraction and it also has attracting energy. Next comes volume correction of real gas. When n mole of a gas are placed in a container of volume V, the space in which the molecules are free to move is equal to V. If the volume occupied by the molecules themselves is negligible, since the molecules have a finite size, the actual volume available to them for their movement would not be V, but less than V. If V is the effective volume per mole of the gas, then this volume must be subtracted from the total volume in order to get the actual volume for their movement. Therefore, V ideal equal to V minus V. For n mole of the gas, V ideal equal to V minus NV. V is also sometimes called the excluded volume and is usually treated as a constant and characteristic for each gas. Next comes pressure correction. Consider a molecule in the interior of a gas, figure 2.18. It is surrounded uniformly by other molecules so that there is no resultant attractive force on the molecule. However, as it approaches the wall of the vessel, the uniform distribution of molecules around it is disturbed and it is now attacked by molecules from one side only. The molecule will thus experience a net inward pull, figure 2.18. Hence, it will strike the wall of the vessels with lower velocity. Measured pressure P will thus be less than the ideal pressure. It is therefore necessary to add a correction term PA to the observed pressure in order to obtain the ideal pressure. Corrected ideal pressure equal to P plus PA. The net inward pull experienced by the molecules about to strike the wall of the vessel is proportional to 1. The number of molecules in the bulk of the gas, and 2nd, the number of molecules striking the wall per unit area at any given instant. Next, both these factors proportional to the number of molecules per unit volume N by V, where V is volume occupied by n moles of the gas. Hence, the correction term PA is PA proportional to N by V whole square. PA equal to AN square by V square, where A is the constant proportionality. Therefore, the corrected ideal pressure P ideal equal to P plus A square by V square. Hence, the product of ideal pressure and volume given by the respectively equations become P plus N square by V square into V minus NV equal to nRT. This is van der Waals equation. Next comes the compressibility factor. The compressibility factor Z is a useful thermodynamic property for modifying the ideal gas law to account for behavior of real gas. It is a measure of how much the thermodynamic property of real gas deviates from those expected of an ideal gas. The closer a real gas is to its critical point or to its saturation point, the larger are the deviations of the gas from ideal behavior. The ratio of observed product of pressure and volume PV to product of pressure and volume of an ideal gas is known as compressibility factor Z. So Z equal to PV observed by PV ideal equal to PV observed by nRT. We know PV ideal equal to nRT. For ideal gas, PV observed equal to nRT. So Z equal to nRT by nRT equal to 1 and is independent on both pressure and temperature. But for real gas, Z doesn't equal to nRT. As for real gas, PV observed does not equal to nRT. So Z will depend on both pressure and temperature. Next comes Avogadro's curve. The ideal gas law equation PV equal to nRT is not obey most gases, particularly at high pressure or low temperature. This was experimentally established by Regnald, Avogadro and others. Only hydrogen H2 and helium H baffle this movement, and the curve rise with the rise of pressure P from the very beginning. The ideal gas law can be derived by means of kinetic molecular theory by making two very significant assumptions that are not proper for real gases. One, there is no attractive force between gas molecules. Second, the gas molecules have no volume. During the 19th century, Avogadro shows that the product of P and V, that is PV, is not quite independent of P. Even for gases like H2O2, N2, etc., this is contrary to Boyle's law. The nature and magnitude of the deviations are clearly demonstrated from a plot of PV against P as in figure. These curves are known as Avogadro's curve. In these curves, PV and arbitrarily temperature of the experiment, yet a gas obeyed Boyle's law, the curves would be horizontal lines with a constant ordinate equal to RT. At constant pressure, the plot for Z versus P, that is vary the temperature for N2 gas. With increase of temperature, dip in the curve decrease, and position of the minimum moves to left. At a certain Tz, minima vanishes. Critical phenomena. When a gaseous system is transformed to its liquid state, there is a tremendous decrease in the volume. This decrease in volume can be effectively brought about by lowering of temperature or by increased pressure, by both. In both these effects, the gaseous molecules come closer to each other and experience on an energy an increase in force of attraction, which results in liquefaction of gases. At any constant temperature, when pressure is increased, volume is decreased, and vice versa. Critical temperature Tc. Every gas except ideal can be liquefied with rise of pressure and decrease of temperature. The temperature above which a gas cannot be liquefied, provided greater amount of pressure, is called critical temperature Tc. Critical pressure Pc. At critical temperature, the minimum pressure which is required is qualify a gas is called critical pressure Pc. Critical volume Vc. At critical temperature and critical pressure, the volume of a gas is called critical volume Vc. Next comes critical phenomenon of CO2. The importance of critical temperature of a gas was first discovered by Andrews in his experiment on pressure volume isotherms of CO2 gas. At a series of temperatures, the isotherms of CO2 determined by him at different temperatures are shown in figure. Consider first the isotherms at the temperature 13.1 degrees centigrade. The point A represents CO2 in the gaseous state occupying a certain volume dimensions as is indicated by the curve AX. At AX, liquefaction of gas commences and therefore thereafter a rapid decrease in the volume takes place. At the same pressure, since more and more of the gas is converted into the liquid state at Y. At Y, the gas becomes completely liquefied. After Y, the increase of pressure produced only a very small decrease in volume. The isotherms at 21.5 degrees centigrade shows that the decrease in volumes becomes smaller because higher the temperature, greater is the volume. Therefore, more pressure is applied to decrease the volume. This effect makes liquefaction to commence at higher pressure compared to the previous isotherms at 13.1 degrees centigrade. At still higher temperature, the horizontal portion of the curve becomes shorter and shorter until at 31.1 degrees centigrade at reduced to a point temperature 31.1 degrees centigrade is regarded as the critical temperature of CO2. At this temperature, the gas passes into liquid imperceptibly about 31.1 degrees centigrade. The isotherm is continuous as CO2 cannot be liquefied above 13.1 degrees centigrade, no matter how high the pressure may be. A gas is said to be at its critical state when its pressure, volume, and temperature are Pc, Vc, and Tc. Next and last conclusion. There is no such thing as an ideal in the world. Nothing is ideal except God himself. So there is no such things as ideal gas. In fact, all gas are real gas. Thank you.
Thank you, Shanago. Now you can mute yourself. Is there any question about this topic?
Yes, I have some not only questions. I have a suggestion to the Sharnavo. First of all, Sharnavo, I just want to point out that there is no connectivity any slides in your any slides. Suddenly you started the critical phenomena. Suddenly you started Amagat's curve. Suddenly you started the compressibility factor. I told you how to connect each and every slide. And another point, whenever you are asking about the real behavior, you just telling that real, ideal pressure and ideal volume. Why ideal? That will be original, not ideal. I told you much more time. It is not ideal, it is original. Whenever you are asking about that original pressure, that is P original equal to PA plus A by V square. And A is not a proportionality constant. You just tell going past just mismatch আর কি. I told you that it is not proportionality constant. It has a meaning. And V, why V square? Because the PA, it is dependent on the density of the both types of the molecules, which one types of the molecules which are attracting to the walls during the collision, and another types of molecules which are going to the walls, but another types of the molecules attracting themselves. এই দুটো different molecular density উপর dependent. That's why it is V square. And K is the proportionality constant, not A. And I could not find any connectivity in each and every slide. And you totally got tensed. So, okay. যা মানে বলেছো ঠিকঠাক, কিন্তু প্রিপারেশন ঠিক হয়নি। আমার মনে হয় না কোনো স্টুডেন্ট এটা বুঝতে পেরেছে যে আইডিয়াল বিহেভিয়ার কি, রিয়েল বিহেভিয়ার কি। দের ইজ নো কানেক্টিভিটি, দের ইজ নো ডিফারেন্স। ইউ জাস্ট মানে টকিং অ্যাবাউট দ্য রিয়েল নেচার, আইডিয়াল নেচার, বাট হোয়াই রিয়েল is different from the ideal. There is no connectivity, there is no reason I found. Okay, I'm not asking any questions, but it is your suggestion. Okay,
Sorry, ma'am.
continue. Okay, Devilina, continue.
Thank you, ma'am, for your suggestion. I believe it will help us also. So our next and last participant is Papu Mondol from semester 1, and this topic is Journey of Periodic Table from Mendeleev to Bohr. You can continue.
দেখা যাচ্ছে?
Yes.
Okay. Good afternoon, everyone. I am Pappu Mondal, a student of Navadip Vidyasagar College, and I am in first semester, Department of Chemistry. Today, I am going to present my seminar, which topic is Journey of Periodic Table from Mendeleev to Bohr. So let's start. Introduction. Chemistry involves study of the elements, now more than 100 in number, and their compounds which are beyond continuing as in all other fields of science. In this case also, generalization of facts stands essential for systematic study of the subject. Thus, periodicity in properties expressed in different ways gave rise to a number of approaches to classify the elements, each with an attempt to study the essentials of chemistry in a very compact and readily accessible form. Next, Mendeleev's periodic table. Mendeleev believed that atomic mass of element was the fundamental property in classifying elements. His law is known as Mendeleev's periodic law. The physical and chemical properties of elements are a periodic function of their atomic mass. The tabular arrangement of the elements are based on the Mendeleev's periodic law is called Mendeleev's periodic table. Here we can show Mendeleev's periodic table, which has 7 periods and 8 columns. Next, advantages of Mendeleev's periodic table. Mendeleev was the first one who wanted to establish a systematic arrangement and bring out the periodicity of properties of elements with atomic weight and propose a periodic law. Number 2, it could point out the incorrect atomic weight of some elements known at the time. Next, drawback of Mendeleev's periodic table. Position of hydrogen. Hydrogen is placed in group 1, however, it resembles the elements of group 1 as well as the elements of group 7a. Therefore, the position of hydrogen in periodic table is not correctly defined. Number 2, position of isotopes. Isotopes are the atoms of the same element having different atomic masses but some atomic number. Therefore, according to Mendeleev's classification, these should be placed at different places depending upon their atomic masses. Number 3, analogous pairs. In certain pairs of elements, the increasing order of atomic mass was not obeyed. In these cases, Mendeleev placed elements according to similarities in their properties and not the increasing order of the atomic masses. Next slide. Moseley's periodic. Moseley found that there was a relationship between wavelength and atomic number. Mendeleev and Moseley are credited with being most responsible for the modern periodic law. When elements are arranged in order of increasing atomic number, there is a repetition of the physical properties. Here we can show the modern periodic table, which has 7 periods and 18 columns. So next slide, Bohr's periodic table. Bohr created his own periodic table in 1922 based on his experimental measurements of electron energies. Board stable added elements discovered since 1869, but it was still, in essence, the periodic arrangement that Mendeleev has discovered. Here we can show Board's periodic table, which has again 7 periods and 18 columns. Merits of Bohr's periodic table. Bohr's atomic model explained the stability of an atom. According to Bohr, an electron revolving in a particular orbit cannot lose energy. Therefore, emission of radiation is not possible as well as long as the electron remains in one of its energy levels, and there is no cause instability in his model. Thank you, everyone.
Thank you, Papu. Now you can mute yourself. Is there any question? Okay, I think there is no question. So that's it for today's program. I hope you all enjoyed it. I would like to thank you all for being patient. Your presence makes us feel grateful. From today's program, we learned something new. Thanks to our principal sir to give us his precious time for his busy schedule. I would like to thank our teachers who helped us to collect materials for this program. It is such an honor for us. I'm so grateful that they always encouraged us and never get tired to taught us such amazing things. Without their help, it hadn't been possible. And thanks to our laboratory staff for providing us our necessary materials. And at least I would like to thank our classmates who always motivate us. Thank you all from bottom of my heart. We will never forget this beautiful evening. Have a good day.
Thank you all for participating in the seminar. ম্যাডাম আপনি কিছু বলবেন?
আগে তোমরা কিছু বলবে কি? তাহলে তোমরা বলো, তারপরে আমি না হয় বলি, because I am the oldest person.
No, it's not formal. No, actually, a very nice presentation by all of you. সবার presentation খুব ভালো হয়েছে, and technically all of you have performed very well, and of course the conducting part was also very good by Nilanjana and Devolin, of course, and all the participants have learned a lot from their presentations, that how to present their work, how to make presentations, and obviously how to get some new ideas out of the syllabus and to learn something new. So hopefully this is the first time we are trying this in the online mode because of this pandemic situation, and let's hope that whatever be the situation, we will continue with this kind of seminars amongst us in our department. Okay, so great job by all of you. I thank you all for the effort you have given for making this seminar a success. Okay, thank you.
Thank you, sir.
Thank you, sir.
সোমা বলো কিছু, সোমা, মনীষা।
কি বলবো জানি না, but it is nice presentation, and Devolin and Nilanjana very well done their job. Appreciate to her.
Thank you, ma'am.
Both, and my two students, I mean third semester and fifth semester, they're Damayanti Roy and Shreya Dev, and also another first semester students, Swarnabhu, they have done well. And because I was totally unable to help them, I know it is my deficiency, but they tried their best, and of course I feel very happy that they tried lots of work. And whenever they ask me that madam, please help me, please supply some materials, but I was totally unable, and it is my deficiency. I of course happy with them that they tried to collect every materials from the network, and they this all to the girls and share them. Whenever I ask them, give a demo, and they already prepare. And I ask within 10 minutes, and ask within 5 minutes, are you ready? Are you ready? Give me some demonstration. And they always reply me, yes, ma'am. And I have to thankful with them that of course they got lots of experience in the last both years, I think. So thanks all of you, and Sornabo, don't mind it. Okay, it is my suggestion because you are first semester student, so you don't have lots of experience, but you should collect. Okay, whenever I'm telling about you that it should be connectivity, there should be connectivity in each and every slide, you should take care. Otherwise, everything is fine. Small mistakes are there, so it will be correct. Okay, don't mind it. It is just my suggestion. Okay, and I'm here also with all of you, and very nice presentation. And it is the first time online mode seminar presentation, so I'm getting much tensed about your presentation. So you people also be so okay, fine. And Devlina and Niranjana, again, thanks and best of luck for your future presentation and conduct very lots of presentations. Okay, and that's all.
Thank you so much, ma'am.
Thank you, ma'am.
পঙ্কজ আছো কি? পঙ্কজকে কিছুক্ষণ আগে দেখেছিলাম।
আমি ওদের সেমিনার শুরু হলে আমি এটা শুধুমাত্র আমার আজকের নয়, আমার সিনিয়র জুনিয়র বা আমার স্যারের যদি প্রেজেন্টেশন থাকতো, আমি অলওয়েজ টেন্সড হয়ে যেতাম, যে মানে আমাকে দেখে লোকে ভাবতো যে আমার প্রেজেন্টেশন কিনা, ঠিক আছে? তো মনে হতো যে কিভাবে বলছে, কোনো জায়গায় ভুল হচ্ছে কিনা। বাট মানে বাকি দুজন তো খুবই ভালো বলেছে। শ্রেয়া স্বর্ণভ একটু ছোট, প্রথম ও একটু